All right, in this video, we're going to look at derivatives of exponential functions. Specifically, we're talking about exponential functions where the base is the natural exponential. So we are looking at functions of this form, e to the x. And so using first principles to justify the derivative for this particular function is a little bit tricky. So I'm going to cheat a little bit, and we are going to use GeoGebra instead. In this GeoGebra file, I have graphed the function y equals e to the x, and I've also plotted a point of tangency, which you can see right here, and I have also graphed the tangent line to that point, which you can see in kind of the light blue purple color. You'll notice I've put here the coordinates of the point of tangency, and here's the equation of that tangent line. I want you to look at the numbers that are presented there, and I want you to see if you notice anything as I move that point of tangency along. If there's anything that's happening between that point of tangency and the equation of the tangent line, where you're noticing a commonality. And so hopefully I've given you enough evidence to see it. You should have been able to observe that for every single spot where I put this point of tangency, the y value of the function is actually the slope of the tangent line. So let's think about what that means for a second. We notice that the y value of this function was the same as the slope of the tangent line, which comes from the derivative at a specific value of x. And so what that means, essentially, is that the exponential function e to the x is actually its own derivative. So d by dx of e to the x, it's just our way of writing a derivative here, is equal to itself. Which is really interesting because that's the first time we've seen a function where that was true. We have not come across any other function where it is its own derivative. And so this is a really interesting property, and it makes these derivatives neat to work with and also kind of easy to work with, because it's not so much the derivative rule itself that you have to keep in mind. It's actually all the other stuff, product rule, quotient rule, chain rule, that you'll have to remember. So let's look at finding the derivative of some functions of that form. Okay, we'll start with these three. We have f of x is equal to e to the 2x, g of x is equal to e to the x cubed, and h of x is equal to e to the x squared minus 2x. When I go to take the derivative here, the key is that an exponential is its own derivative. So when I go to write out f prime for this first one, I'm going to just write it out again. That function is its own derivative. Now, this is the result of a composition. That 2x is a function within a function. So I do have to account for chain rule and multiply by the derivative of that inner function, which would be 2. So I end up with the derivative here is 2 times e to the 2x. If I move on to b, the derivative here is again just going to be the function itself. But then, because it's a composition, I have to multiply by the derivative of the inner function. So I have 3x squared multiplied there at the end, which I could, if I felt so inclined, rewrite this way. And for h, same idea. The derivative of h is itself. And then, because it's a composition, multiplying by the derivative of that innermost function. So 2x minus 2 is the derivative of that exponent. And so I could write it out like this. Probably wouldn't multiply that out, even if you might be tempted to. It doesn't actually simplify anything any further. So the question then becomes, what do you do if you have a function that the base isn't e? So if I have an exponential and the function is 2 to the x, this rule doesn't seem to hold true anymore. We said very clearly the derivative of e to the x is e to the x, but that doesn't mean that the derivative of every other exponential function is itself. So we kind of have to figure out a way to work around that. Now, when we studied exponential functions in DP1, we spent a lot of time looking at how you could write exponentials in different bases. So if I wanted to rewrite 2 to the x in base e, I could rewrite it as e to the ln of 2 to the x. And so that's just one of those rules that's in our formula booklet where we have something like log base a of a to the x is equal to x, which is equal to a to the log base a of x. It's basically telling us how we can introduce logarithms as long as we put the exponential in there at the same time, because they're inverses of each other. So by putting e to the ln of something, those would typically cancel out and I'd just be left with 2 to the x. However, this allows me to rewrite it in a way that's really handy, because I can use my log law to bring that x down in front of the ln 2 and write it like this. And maybe you don't see why that is necessarily very helpful just yet, but let's look at what happens when I go to take the derivative now. Because it is base e, I can write the derivative as itself times the derivative of the exponent. Now, when you look at x ln 2, some of you might be scratching your head and say, wait, I don't know how to do the derivative of ln yet. But remember, ln 2 is just a constant. So really, you should be looking at this part here as if it's ln 2 times x, just a number times x. And whenever you're asked to take the derivative of that, it's just the coefficient in front of x. So ln 2 is the derivative of my innermost function when I'm using chain rule here. And so my final derivative of j then would be e to the x ln 2 times ln 2, or if I sub that 2 to the x back in, because I know that this part here is equivalent to this part here, I can therefore replace this with 2 to the x. And so I get that this is actually the derivative. In general, if you wanted to find the derivative of anything that was base a, the derivative of any exponential that's base a is actually just itself, but times ln of a, which is really handy to know, although not actually required in a lot of questions in standard level. Okay, let's look at some more complicated examples that introduce product rule and quotient rule. So I've got 2 here now, and I'm switching to Leibniz notation. The one on the left I'll use product rule on, the one on the right I'll use quotient rule. So I'm going to split it up into pieces just for those of you who are still comfortable with that way of looking at products and quotients. So my first function here in the product is x squared. My second function v is e to the 2x. The derivative of u, which I'm just writing as u prime, you could also write it as du by dx. Actually, maybe let's do that. My derivative of u is going to be 2x. My derivative of v, dv by dx, is e to the 2x times 2, which I could simplify, but I'll worry about that in a minute. And so now if I go to stick the pieces back together, I have to remember the derivative of the whole function will be u times dv by dx plus v times du by dx. So we're just kind of mixing and matching the function of one, the derivative of the other, multiply them together, and then do the same thing with the other term. U is x squared, dv by dx is 2e to the 2x, so I've just simplified it there. V is e to the 2x, and du by dx is 2x. And so if I go to simplify this a little bit, this is one of those rare instances where normally I would say not to worry about simplifying, but if you look here as I write it out, there's actually a lot I can common factor between those two terms. I can factor out a 2, I can factor out an x, and I can factor out an e to the 2x. So if I pull all of those things out in front, what's left behind from the first term is an x, and I've actually factored out everything from the second term, so that leaves behind a 1. This is one of the rare instances with exponentials base e, where factoring the derivative at the end is actually a little bit cleaner to do, and certainly worthwhile. All right, let's move on over to the quotient rule question. I'm going to do the same thing. I'm going to split it up based on the top and the bottom. So my top function, u, is e to the negative x. My denominator function, v, is x cubed. And so the derivative of u is negative e to the negative x. I simplified that one right out of the gate. Hopefully, as you get more exposure to this, you'll be comfortable doing the same. The derivative of v here is 3x squared. And so we're all set to assemble things here using our quotient rule, which tells us that it's the derivative of the function is v times du by dx minus u times dv by dx all over v squared. And so we get x cubed for v, du by dx is negative e to the negative x. And then I'm going to subtract e to the negative x and 3x squared. And all of this will be divided by x cubed and then squared again. This one will tidy up a little bit here. The numerator ends up being this, negative x cubed e to the negative x minus 3x squared e to the negative x. You're going to notice there's a lot that can factor there. And in the denominator, I have x to the 6. Now, if I look at what can factor on top and bottom, it appears I could factor out a negative x squared e to the negative x from both terms. That's going to leave me with an x here. And from that second term, it's going to leave me with a 3. This is all over x to the 6. And then I can actually reduce here, which might be worthwhile depending on what the next thing you have to do with this is. So if I reduce those x squared and x to the 6 together using exponent laws, I'm going to be left with negative e to the negative x times x plus 3. And this is all over x to the 4. And so in the grand scheme of things, taking derivatives of exponential equations, when they're base e, it's actually quite straightforward. If anything, I think you'll find working through these exercises, you're getting more practice with product rule and quotient rule than anything else. And so derivatives of exponentials tend to be pretty straightforward that way, as long as you remember that the derivative is itself times essentially the derivative of whatever the exponent is, then you are all set. So we'll end this video there. There's a second video up for derivatives of logarithms you're going to want to check out. Make a note from that.